Okay, we're going to do some problems that involve velocity selectors. We've got an electron traveling through this magnetic field, and it does not get deflected. It doesn't curl up, it doesn't curl down. Well, that's kind of curious, isn't it? I mean, if the electron passes through, well, it's going to feel a magnetic force. You know, we could use our left hand, stick our thumb this way. We could figure out where the field lines point. It's out of the plane of the page, so our fingers would stick out like this, and our palm would be facing up. So the electron, when it's passing through, definitely does feel an upward magnetic field force. Why doesn't it curl up then? The answer is because it also feels a downward electric force. It has to. And that downward electric force must be canceling out the magnetic force. So, okay, negative electron is attracted to positive, so there must be positive charge on this plate down here, and there must be negative charge on this top plate, repelling the electron. So there's a special magic speed at which, what's the speed at which the two forces perfectly cancel out? Well, I could plug in QVB on the left, and I could plug in Q times E on the right, because electric field strength, we recall, is electric force per coulomb on a small positive test charge. And the Q's, this is interesting, Q's cancel out, and if I solve for V, isolate V, I see it does not matter what the mass is, what the charge is, or anything else about the particle. As long as you have this speed, it will be true that the two forces cancel. So this alpha particle, it has a charge, positive 4 times the elementary charge. It has a bigger mass. It has 4 times the mass of a proton, which is way bigger than the mass of an electron. But those facts do not matter. All that matters is whether or not you have the same speed that passes through undeflected. This is the one and only value of speed where you pass through undeflected, and so every particle needs to have the exact same value to pass through undeflected. And yes, in fact, the alpha particle does have the same speed, so it will similarly be undeflected. You could send something through with the same speed, and it could have any charge, positive 24, negative 11. It doesn't matter. All that matters is the speed. On to the next one. We have a proton. Oh, let me circle that. The data booklet tells me its mass and its charge traveling to the right with a horizontal speed of this, and it enters a uniform field of strength E. So before I do anything else, these field lines tell me where a small positive test charge is pulled. This is a positive charge, so it will be pulled with the field line. There's the electric force, or I could call it the Coulomb force if I wanted. We've used that as well. The strength of the field is 2 times 10 to the third. It's directed downwards. Calculate the magnitude of the electric force on the proton. The magnitude of the force, well, I know E, I know Q, and I'm looking for force. They are related by this equation. The value of E is given, Q is known, so force is going to be the product. That's going to give us 2 times 10 to the third. And E, that's the value of E. The value of Q is 1.6. So 2 times 16, that's 32. I've got 10 to the 3, 10 to the minus 19. I add the exponents, and there's my answer. A uniform magnetic field is applied to the same region, here. A second proton enters at the same spot with the same velocity, which was this. And let's see, it continues to move horizontally. Well, wait, if it feels this downward force, shouldn't it go down? The only way to make it move horizontally is if we have a second force pointing up. And where does that force come from? It's a magnetic force. So that magnetic force has to be just as strong as that Coulomb force, right? 3.2 times 10 to the minus 16. That will be important. They want us to find the magnitude and direction of not the force, but the field itself, B. To find the direction, we need the right-hand rule. I stick my thumb, I use my right hand, it's a positive charge. I stick my thumb with the velocity. I have to face my palm upward, and the only way to get my palm pointing up is if my fingers stick into the page. All right, next I need the magnitude of B. Well, I know B shows up in this equation. Can I calculate the value here? Well, I do know force. I said it's the same as the Coulomb force. I know the charge of the proton, and I know its speed right there. So we plug in values, we solve. We're going to need the force on top. I need Q and V on the bottom. 1.6 times 10 to the 4. And this is going to be, let's see, 3.2 over 1.6 squared is 1.25. My decimal point is right here for now. But then I've got negative 19 and 4 makes negative 15. They come up, and the sign flips to positive 15. And then I've got negative 16 and positive 15, so just times 10 to the minus 1. But instead of writing that, I can just move the decimal over. So 0.125. The unit is Tesla. I hope that's right. Part 2, B2. An alpha particle. Remember, an alpha particle just has a bigger charge and a bigger mass. It enters the region at the same point, moving with the same velocity. Ooh, same velocity. Will it move in a straight line? Yes, because it has the same velocity. And the velocity at which particles aren't deflected is, if we recall, is it E over B or B over E? I always forget. Well, we can just do it again, calculate. Oh yeah, V is on the same side as B, so I have to divide by B. So it's going to be E over B. We haven't changed the value of E. We haven't changed the value of B. So the selected velocity is the same. Moving on. Protons traveling with the speed of this enter the region between the charged plates. Okay. This thing doesn't have any charge because it's connected to the Earth. It's kind of grounded, as we say, but there's a positive charge here. So shouldn't protons feel a downward Coulomb force, a repulsive force? Yes, and they do. But that means they have to feel something pointing up, canceling the force, and allowing them to move without any deflection. No deflection. What's that coming from? Where is that second force coming from? It's a magnetic force. State the direction of the magnetic field. Okay, my thumb points with the velocity. My palm faces upward like this. Oh, it's the same as the last one, isn't it? This is velocity, that's force. And so this would have to, my fingers would have to point into the page. No, that was too easy. It was the same. The strength of the field is this value. Determine the magnitude of the strength of the magnetic field. That's the value of B. Determine the magnitude of the electric field strength, E. Okay, well, look at how many points this is worth. I better start by saying that the two forces are equal. That's going to be important. And I'm just going to make this whole thing easier by flipping the two. The electric force divided by the charge is equal to the field strength. Well, okay, hang on then. I could plug in for electric force Q times the electric field strength. And the magnetic force is QVB. There is a sine theta, but we see the charge is moving to the right, and the field is pointing perpendicularly into the page. So we have sine of 90. The angle is 90 between the velocity and the field. And sine of 90 is just 1. Okay, I cross out the Q's, and I get E is equal to VB. We have both of those values. V is 3.9 times 10 to the 6, and B, the strength of the magnetic field, is 2.3 times 10 to the minus 4 Tesla. When we do this calculation, 3.9 times 2.3 is 8.97. And I've got positive 6 here, negative 4 there. I combine those exponents, I add when I multiply, and that's going to be 10 to the 2. So I'll just move the decimal over 2. Newtons per Coulomb. A lot of mental math in this video. Hopefully it's right. But if not, there's also a key posted.